So here we're going to discuss alpha decay. An alpha particle, and we use the Greek letter alpha to indicate this, is equal to a helium nucleus. So a helium nucleus has 4 particles in total, 2 of which are protons. So down here is a little bit of review. This is the number Z, and that is the number of protons in the nucleus. And then up here we have the letter A for atomic weight. So that is the atomic weight or the atomic mass of a nucleus. And that A value would be equal to Z plus the number of neutrons. So if we have a total of 4 particles, that gives us an atomic weight of 4. And with 2 neutrons, we must also have two protons. We must also have 2 neutrons in the nucleus. So that's an alpha particle. Alpha decay is something like this. If we have the nucleus of some atom, let's say this is a nucleus here, alpha decay means that an alpha particle will be calved off of that nucleus and will be ejected from the nucleus. So we can grab anything we like. We'll just take these guys over here because they happen to be convenient. This here is the equivalent of a helium nucleus. We have 4 particles total. Let's draw a little map here, or a legend. We'll just let the white fellows be neutrons, and then the red fellows can be protons. So in this diagram here, we have 2 protons, 2 positively charged particles, and 2 neutrons. And giving us the sum of those together, we have in this area here the equivalent of a helium nucleus. So if that is capped off and all we're left with is just the rest of this material here in the nucleus, if this is all that's left, then what would happen to this material? Well, A would be decreased by 2. So A is decreased by 4. We've lost 4 particles, so we'll have an atomic weight that is lower by 4, and then the Z value, the number of protons, decreases by 2. So let's give a couple of examples of this. We'll erase the chalkboard here. So let's say we have something like Neptunium, Np, and it has an atomic mass of 237, and it has 93 protons in its nucleus. It can decay into protactinium, written as Pa, with 91 protons in its nucleus, and then 233 as a total atomic weight. And then what would be ejected here would be an alpha particle, and we'd write it like this. So we have this fellow decreasing by 4, and then this is decreased by 2. Here's another example. We have samarium-147 with an atomic number of 62. It can decay into neodymium-143, which has an atomic number of 60, and that would be plus alpha. For both of these, there would also be some energy released, which we can write as plus Q. We're not too concerned about that. Again, the atomic number decreases by 2. The atomic mass decreases by 4. And then just as one last example, samarium comes in various flavors. There's also an isotope of samarium with an atomic weight of 46. Also an atomic number of 62, as it must. If we had any other number besides 62 here, we would not have samarium. The only reason for writing this is just for accounting purposes. We write neodymium here with an atomic weight of 142, and since it's neodymium, it must have a Z value of 60, so we'll write plus alpha and plus Q to just make this complete. Again, we're losing 4 particles total from the nucleus. 2 of them are protons, so that goes down by 2. So these are examples of alpha decay. We'll take a look at other examples of alpha decay or combinations of alpha decay in another video.